I've done about 70 to 100 interviews for various mechanical engineering roles across the United States and China at startups, medium-sized, and global 500 companies. As you can imagine, I've been asked all kinds of different questions. Some were easy, but the majority of them were pretty challenging. There were even a few that were irrelevant to the role. So in this video, we're gonna walk through and answer the most commonly asked mechanical engineering interview questions based on my experience. If you have an interview coming up soon for a mechanical engineering internship or full-time position, be sure to watch to the end because I'm gonna help you ace your next interview. So I like to sort all interview questions into three broad categories. First is general non-technical questions. These are more open-ended questions that help the interviewer understand you as a person, your motivations, and your career goals. Tell me about yourself and why do you want to work for us are two examples of general non-technical questions. The second is, of course, technical questions. These test your skills and knowledge by asking you to apply math, physics, and engineering principles to solve a problem. Some examples could be perform a tolerance stack-up analysis on this assembly. What are the advantages and shortcomings of injection molding and 3D printing? When does it make sense to use injection molding over 3D printing and vice versa? Third is behavioral questions. These focus on how you would react and behave in specific situations and give insight into things like your personality, leadership, problem-solving skills, teamwork, and adaptability. A classic question is, can you give an example of a project where you had to meet a tight deadline and what was the outcome? Sometimes a question could be both technical and behavioral. Tell me about a time you faced a design issue with a mechanical system or component. How did you diagnose the problem and what steps did you take to resolve it? So the questions we'll discuss now are mostly technical with some behavioral elements in them. I'm sure you guys will have no problem with the general non-technical questions, which are a lot more straightforward and easier to answer. So question one is purely technical. Explain the stress strain curve, including the key regions, and describe what happens during loading and unloading of a material. How does this relate to elastic and plastic deformation? This question is relatively straightforward. If you've taken material science, you shouldn't have any problems answering it. So the stress strain curve of a material is obtained by performing a tensile test. It has two regions, elastic and plastic. In the elastic region, which is linear, stress strain are proportional to each other and is governed by Hooke's law, which states that stress equals Young's modulus times strain. The slope of this line is Young's modulus, which represents a material's stiffness. If a specimen is unloaded at any point in this region, it will return to its original length and follow the same trajectory if loaded again. If we load the specimen past the proportionality limit represented by P, which is the max value of stress at which the stress strain curve is linear, will reach the elastic limit or point E. This represents the max theoretical value of stress at which there is no permanent deformation. Even though the curve is not linear between point P and point E, the material is still elastic in this region. Once past point E, we enter the plastic region where the specimen will undergo plastic or permanent deformation. Shortly after, the yield point or point Y is reached, which represents the stress at which a small specified amount of permanent deformation happens. This stress is referred to as the yield stress. For materials without a well-defined yield point, it is defined using the 0.2% offset method, in which a line parallel to the linear portion of the curve is drawn that intersects the x-axis at a strain value of 0.002. The point at which the line intersects the stress strain curve is designated as the yield point. So the yield strength is often used in design calculations. If we continue loading the specimen, we'll reach point U, or the ultimate or tensile strength of a material, which is the max value of stress on the stress strain diagram. After reaching the ultimate stress, specimens of ductile materials will exhibit phenomena called necking, in which the cross-sectional area in a localized region of the specimen reduces significantly. Finally, we reach point F, or the fracture point, where the material fails and separates into two pieces. Now, to answer how the material would behave when unloaded and then loaded in the plastic region, let's just say it was unloaded here at point Z. After unloading the material will follow the unloading line parallel to the original, but the plastic strain will remain. So if we load the specimen again, it would follow line QZ, which is the unloading line, and continue until point F, or fracture. Notice that point Z is now the new yield point, which is higher than the original yield point Y. This is due to strain hardening that occurred by loading the material beyond the elastic limit. Now, it's likely that the question will ask you to calculate specific numbers or derive an expression for the elastic and plastic strain of the material. So the elastic strain can be calculated easily using Hooke's law, where epsilon sub E is equal to the stress at this point over the elastic modulus. With the elastic strain, we can calculate the plastic strain by subtracting it from the total strain. Obviously, there's a lot more to the stress strain curve, but if you can mention all of the points we covered, then the interviewer should be satisfied. You should also familiarize yourself with the stress strain curves of common engineering metals, polymers, and ceramics, and the differences between them. Based on my experience, companies like to ask about the important material properties like elastic modulus, yield strength, and the ultimate strength of certain materials like steel, aluminum, and nylon. Now, a good thing to note is that the total area under the stress strain curve represents the total energy absorbed by the material up to fracture. This is also known as a material's toughness, which is an important material property for applications requiring high energy absorption before failure, such as impact resistant composites used in a car's chassis. All right, now the second question is very important, but is oftentimes downplayed or overlooked. Tell us what you know about our products. Now, this question is technically a general, non-technical question, but if you can nail the answer and make it technical, it can be a difference maker in landing the job. Don't give a generic answer like, I know you make a lot of cool products, or I looked on your website and I know you make a lot of premium laptops. The interviewer is asking this question to probe if you did your homework and to test your ability to connect your skills and expertise with the company's offerings. Show that you can relate their products to your skills and background. Specifically focus on how their products incorporate good design principles, materials, and manufacturing processes, or you can even talk about how you would improve the design. You can express interest in a specific product because it uses cutting-edge engineering or technologies that align with your background. You could also point out that product X presents engineering challenges that you're familiar with or excited to work on, such as testing, quality control, or optimization. So if you're interviewing for I don't know, product design or mechanical engineering related role at a consumer electronics company like Apple or Samsung, you could say, I've been following your company for a long time and I'm really impressed by your latest smartphone, the Galaxy S25 or iPhone 16. The new heat management system design, which incorporates advanced materials like graphene and contributes to a 15% increase in battery life, is an incredible innovation. With my background in thermal analysis, simulations, and material science, I'm confident in my ability to push the boundaries of similar innovations in Samsung's or Apple's products and help the company achieve its business goals. Question 3 is a technical question related to beams. Interviewers love beams, so pay attention in your mechanics of materials class. Can you explain the difference between shear force and bending moment in beams, and how would you calculate them for a simply supported beam subjected to a uniform load? So in a nutshell, you don't have to say too much here. Shear force is the internal force parallel to the cross section of the beam, and bending moment is the internal moment causing the beam to bend. Mathematically, the shear force at position X, or V of X, is simply equal to the integral of the applied or distributed load W of X with respect to X plus a constant which is determined by boundary conditions. Similarly, the bending moment M of X is equal to the integral of the shear force V of X with respect to X plus a constant. Now, for calculating shear force and bending moment of a simply supported beam with a uniformly distributed load, if you've already memorized the max shear force and bending moment and their locations of such a beam configuration, you can simply directly explain it to the interviewer. However, if you need pen and paper to visualize and explain the steps, there's nothing wrong with that. Just tell the interviewer. Now, I don't want to spend too much time on this, but we can begin by drawing a simple diagram and defining all the parameters. So we'll represent the reaction forces as R sub A and R sub B and the load intensity with W. From symmetry, RA equals RB, which equals the load intensity times the beam length over 2. To calculate shear force, we make a cut at point X. The summation of the forces must equal to 0, and we get V of X equals R sub A minus W times X. The shear force at the left end, or X equals 0, is W times L over 2, and at the right end, or X equals L, is negative W times L over 2. 2. We know the shear force is 0 at the middle, but if you didn't know, just plug in 0 in for V of x and solve for x, which is L over 2. Similarly, for the bending moment, the sum of the moments must equal 0. So m of x plus the moment from the distributed load, which is W times x over 2, equals the moment from the reaction force, which is R sub A times x. Rearranging, we get m of x equals R sub A times x minus W times x squared over 2. The moment at the left end, or x equals 0, is 0, and at the right end, or x equals L, is likewise 0. The max moment occurs at the middle, or x equals L over 2, so we get m of L over 2 equals W times L squared over 8. You could plot the shear force and bending moment diagrams as well if you wanted to, which look like this. Now, question 4 is another beam question. How would you design a beam to minimize deflection under load? This question is fairly easy if you know the parameters that affect deflection. Obviously, the max deflection is different for each load case, but the parameters are all the same. The max deflection of a simply supported beam with a point load is given by the force F times the beam length L cubed over 48 times the Young's modulus of the material E times the area moment of inertia I. So right off the bat, you can reduce the span of the beam since the deflection is proportional to the cube of the beam length. You could also reduce the force, but that's likely out of your control. You can, however, select a stiffer material like steel, whose Young's modulus is roughly 200 gigapascals, over aluminum with a much lower Young's modulus of 70 gigapascals. The moment of inertia I of a rectangular cross-section is given by BH cubed over 12. So increasing the height of the beam will reduce deflection by a significant amount. At the same time, that would add a lot of extra weight. So you could consider an I-beam because it has a high moment of inertia for its weight. Its cross-section maximizes the moment of inertia by concentrating material further from the neutral axis in the top and bottom flanges while minimizing the material near the neutral axis in the web. Now, question 5 is design related. How would you select the appropriate material for a specific mechanical component? So everyone's process will be slightly different, but you should touch upon several key factors that directly affect the performance, cost, and manufacturability of the component. The first step is understanding the specific function of the component and the environment in which it will operate in. I would ask questions like, what loads will the component experience? Tension, compression, shear, and or torsion. What temperature range will the part be exposed to? Is corrosion resistance required? Will it be exposed to chemicals, moisture, and seawater? Does the part need to have high wear resistance? What are the weight and cost constraints? Next, I would choose a material that exhibits the right combination of properties, leveraging some type of material selection tool like mat web. Yield strength, hardness, and fatigue resistance will be key factors if the component will experience cyclic loads or high stresses. If the part operates in high temperature conditions, I will look for materials with a high heat resistance or resistance to thermal expansion. For applications where weight is critical, I would consider lightweight materials like titanium alloys or composites. Once I have a good idea of the required material properties, I would evaluate how easily the material can be processed and manufactured. Can it be machined, welded, cast, or forged easily? Does it require any heat treatment to improve its properties, such as tempering or annealing? Can the material be joined effectively to other materials via welding, brazing, or adhesive bonding? If the part needs to meet specific industry standards like ASTM or ISO, I would choose materials that meet those requirements. Now, before we continue, one of my favorite platforms that helped me prepare for interviews and land more job offers was Brilliant, the sponsor of today's video. It contains thousands of interactive lessons in math, physics, data analysis, programming, and AI. Brilliant breaks down tough problems into smaller pieces with the first principles approach. Their lessons build problem-solving skills by allowing you to experiment with concepts. This method is proven to be 6 times more effective than traditional lecture-based learning. Brilliant's lessons are crafted by professors, researchers, and professionals from MIT, Caltech, Microsoft, and Google, so you learn from the best. Brilliant fosters critical thinking through active learning, not memorization, so you become a strong problem solver. It also encourages a habit of daily learning essential essential to personal and professional growth. Brilliant's fun, bite-sized lessons allow you to learn on the go, anytime, anywhere. One of my favorites is Brilliant's science courses that builds physics fundamentals and uses formulas to solve real-world engineering problems and enhance your problem-solving skills. To try out everything Brilliant has to offer free for a full 30 days, visit brilliant.org/engineeringgonewild or scan the QR code on the screen, or you can check out the link in the description below. You also get 20% off an annual premium subscription. Question 6 is, what are tolerances and how do you determine which tolerances are critical? Can you share an example where tolerances cause manufacturing challenges and how you address them? Tolerances simply refer to the allowable variation in the part's dimensions. Since perfect manufacturing isn't possible, tolerances define the range of acceptable deviations from the ideal dimensions to ensure proper fit and function of the part within the assembly. When deciding which tolerances are critical, I look at what type of fit is required between parts. For example, in mechanical assemblies, fits are categorized as a clearance fit, where parts are designed to have a gap between them, such as a shaft and a hole that need to rotate freely. Second is an interference fit, where parts are intentionally designed to fit tightly, such as a press fit bearing. Third is a transition fit, where parts could have a small gap or interference, and the fit depends on the specific application. A project that I worked on involved an engine block with height, bore, and deck height tolerances. The casting process introduced dimensional variability, which caused issues with the piston fit and cylinder head alignment. We addressed this by reviewing the tolerances, optimizing the casting process to reduce variability, and utilize precision CNC machining to bring the parts into spec, thus reducing scrap and improving overall efficiency. Question 7 is, how would you use numerical simulations to streamline the product development process? At what stages of development would you implement these tools and why? For this question, try to relate it to your personal experience. In the early design phase, simulations can allow for rapid iteration and testing in a virtual environment. This helps us to explore different design options, materials, and configurations that might be too costly or time intensive to prototype physically. It also allows us to optimize geometries and load cases early on. During the detailed design stage, finite element analysis, or FEA, helps refine the design by optimizing the material distribution, weight, and identifying potential weaknesses. This significantly reduces the likelihood of issues during manufacturing and reduces the risk of defects or costly redesigns after product launch. Although simulation tools are not a replacement for real-world testing, it can, however, save significant time and cost by reducing the need for multiple physical tests. I have experience in automotive crash simulations. When designing a new vehicle, automotive manufacturers leverage FEA simulations to simulate crash scenarios like frontal, rear, and side collisions that help assess deformation of materials, the impact on passenger safety, and how the energy is absorbed during the crash. By doing this virtually, engineers can optimize the vehicle structure, crumple zones, and safety features, ensuring that the vehicle meets safety regulations before physical crash testing while speeding up time to market. Question 8 is, can you walk us through a challenging project that you worked on and how you overcame obstacles? For this question, pick out a project that you can speak to and are proud of. Showing enthusiasm and passion can set you apart from the crowd, even if the project itself isn't that impressive. For my master's thesis that I completed at Tsinghua University, I researched the quasi-static and dynamic behavior of steel, aluminum, adhesive, and self-piercing rivet joints for automotive applications, focusing on their performance under a wide range of strain rates. The biggest challenge was modeling their complex and nonlinear behavior in LS-DYNA and coming up with a new and innovative approach. I read through massive amounts of papers, collaborated with industry experts for practical insights, and took an iterative approach, starting with smaller models, and validated my simulations through real-world testing. I also managed tight deadlines by prioritizing tasks and setting realistic unrealistic milestones. The final model significantly improved prediction accuracy, and during my time at Tsinghua University, I was able to publish 3 papers in 3 reputable journals. This experience not only gave me the opportunity to develop a deep understanding of modeling physical phenomena using advanced meshing, filtering, and fitting techniques, as well as automotive manufacturing methods and material testing, but also taught me how to approach complex engineering problems systematically. These are all skills that I'm excited to bring to this role. Question 9 is both a technical and behavioral question. If you've never worked with titanium, how would you go about designing a titanium alloy sheet metal part? For behavioral questions, be as specific as possible and tell the interviewer the exact steps you would take. Don't say something vague like, I would just treat it like designing any other metal part. I'd use the same tools and techniques I'm familiar with for steel or aluminum. Titanium is strong, so I probably wouldn't need to worry about it deforming under load. I design the part, send it to manufacturing, and adjust if there are any issues during production. Instead, a better answer is I would start by researching the properties of the specific alloy, such as Ti6Al4V, to understand its strength, corrosion resistance, and formability. I'd also consult industry standards like ASTM or ISO for design guidelines specific to titanium. Next, I consult with manufacturing engineers or vendors to understand the material's constraints, such as minimum bend radii, spring back, and tooling requirements. Since titanium is less formable than materials like aluminum, I'd ensure the design accounts for these factors, including its sensitivity to galling during forming. I'd use FEA to simulate stresses and deformation during forming to refine the design virtually, and work with suppliers on sourcing the material and optimizing the design for minimal material waste given titanium's cost. If needed, I wouldn't hesitate to reach out to colleagues for guidance on best practices. Finally, I'd validate the design through prototyping and testing, focusing on critical factors like fatigue, corrosion, and thermal performance, depending on the part's use case. Now, for the last question, we mentioned that there's technical, behavioral, and general non-technical questions. Technical questions can be further categorized into engineering related, like beam or design questions, or non-engineering related questions. Non-engineering related questions can be anything from math questions to logic challenges that absolutely have nothing to do with the role. I remember I applied for, I think it was a mechanical engineering role at Procter & Gamble, and they made candidates complete a personality test where they explicitly state there are no wrong answers. But come on, you really think I'm gonna believe that crap? But wait, there's more. Then they ask candidates to complete, in my opinion, a ridiculous assessment where one of the questions, to give you an idea, asks you to memorize the position of a dot on a grid. Then immediately afterwards, they ask you 3 spatial orientation questions in a row, and then ask you to memorize more dot locations before finally asking you to recall all of the dot locations in the correct sequence. To me, these types of assessments are pretty BS. So for question 10, let's just talk about a non-engineering related question that I was asked. Companies that ask these type of questions raise a lot of red flags for me, and I wouldn't want to work for any of them. But I wanted to talk about it so you guys are at least aware and aren't surprised if you guys get asked these type of questions. So question 10 is, how many rotations does circle A make traveling once around circle B? Derive a general equation. So you might have learned in physics or dynamics class that if we assume there's no slipping, the distance traveled by the center of circle A is equal to the amount the circle has rotated. Hence, the number of rotations of circle A is equal to the distance the center has traveled divided by the circumference of circle A. The distance the center has traveled is just 2 pi times the radius of circle A plus the radius of circle B. The circumference of circle A is simply 2 pi times the radius of circle A, and we get this general expression. So let's say the radius of circle A is 1 and the radius of circle B is 2. Circle A would rotate 3 times traveling once around circle B. Alright guys, so these are 10 questions that I think are awesome to add to your arsenal of potential interview questions for mechanical engineering roles. Feel free to share your interview experiences down in the comment section below. I love to hear them. If you're interested, I've also put together a list of 80 mechanical engineering technical questions that I think are great to know and hopefully will help you land your next dream dream job. But keep in mind that the solutions are not included. I'll drop a link in the description below for you guys to check out. As always, thank you so much for watching. If you found this video helpful, be sure to check out my video here where I share a surefire strategy to ace any engineering technical interview, and I'll see you in the next one. Peace.